All right, welcome. In this video, I want to introduce ourselves to a handful or a collection of graph problems. Now, there are numerous graph problems, hundreds of graph problems that you might encounter. I'm just going to try and go through some that I think are the more common ones, and at least ones that I think are some of the more interesting ones. So let's start with some of the simpler ones. Some of the simpler ones just tie back into some of the terminology that I covered in an earlier video. One of the terms that I defined was the term connected. A connected graph is one in which there is a path from every vertex to every other. So this is actually an example of no, this is not a connected graph, since there's not a path from, say, this red isolated vertex to any of the other ones, actually not all of them. But I have colored the different connected components of this graph different colors, so we can see the graph, the subgraph that's all blue. The answer to that problem would be yes if we passed in that subgraph alone. So here I've sort of formalized the problem, and maybe I'll mention for this video and for other videos the way that you will characterize a problem, an information processing problem. Of course, is going to be a relationship between the input and the output. So here we're going to be stating these formally, that is using definitions in math and in the language of math and logic. Here I've actually stated a special kind of problem because the output here is a yes-no problem. This is a special kind of problem called a decision problem, which actually becomes useful when we want to start comparing problems to one another. Most problems can be translated into decision problems. Now, if we look a little bit closer here, this decision problem is just going to tell us if the graph we've got is connected or not. So if it was given this whole graph, it should answer no. Now, we can see that there's sort of a closely related or parallel problem to this, and so I'm going to define it here, where we're given sort of the same input, just a graph, but we no longer have a decision problem here. We're going to have a specific output, which is, I want to kind of, we usually call this sort of decomposing the graph into its connected subgraphs, which we often call connected components. So maybe what we were given is the original graph, the whole thing here, but the output that I actually want you to do is break it down into subgraphs so that each subgraph is a connected subgraph. Now here I'm relying on this concept of partitioning the graph into connected subgraphs, and I'm sort of banking on some of the heavy lifting, the technical work being carried out by this phrase or word here, partitioning of G. What do I mean here? Well, here I mean, of course, that what I'm doing to G is I'm just partitioning the vertices. So I might draw an envelope around these vertices, draw one around this one, draw one around these, and then if I took that and I induced the subgraphs on those, that should capture all my edges. So the E's, the edge sets that we get after inducing this subgraph, should also partition the edge set. So V partitions the vertex set, or VI's will partition the vertex set, EI's will partition the edge set, and that's what we mean by partitioning a graph G. So here again is sort of just a visual depiction of that. Now, of course, if we left out any vertices or we left out any edges, that would not count as a partitioning. And so even if the subgraphs we end up with were all connected, that would not be an acceptable output. We want ones that partition the graph, including all the original vertices and edges. Okay, so we see that these two problems are sort of related to each other. Maybe you might think of one as being easier than the other. We might think of this sort of detection being easier than the decomposition. But it turns out that often when we have these two problems like this, a decision problem variant and a non-decision problem variant, usually we have that the resources necessary to solve one is often the same as the resources necessary to solve the other one, if not completely, at least in one direction. And of course I'll talk more about that in a different video. Here I just want to talk about the different problems, but these two problems are very closely related, and in fact we could solve both of them following a very similar strategy. And so that strategy, if you haven't encountered this before, is we want to do a traversal, and in particular we're going to do a depth first search is going to be a little bit more helpful here. If I start with a random point here, do a depth first search, I should be able to encounter every vertex in the connected component. So if I just want to say yes, no, I run my depth first search. If any of my vertices are not touched, then I'm not connected. If I capture all my vertices, then on the other hand, I must be connected. So depth first search is going to be a good, straightforward solution to the yes-no problem. How does it help us recover the connected components? Well, actually, again, if I do a depth first search, it will grab me all the vertices in the blue set first. So I grab all of them, throw them into one pat, call that induce my edge set from that, and then begin again. Grab a random vertex that I haven't covered, run depth first search again. That will grab me all of the vertices in the next connected component. So often what we would do would just be run depth first search on any of these components. Now here I've selected depth first search. I think it's my preferred one, but a breadth first search would work here as well. Since you'll only be following edges, you will only ever capture nodes within your connected component. So I'm going to say depth first search, but you could, if you prefer breadth first search, you could go ahead and do that too. Of course, the runtime of both is going to be order of the edge set. So a quick solution here. Now, why do I bring this up? These connected questions are actually not often, I wouldn't say that this is a big problem that we face. More often than not, if you have to check to see if a graph is connected, you're probably doing that before you do something else. Or if you're fetching out the connected components, again, that might be a subroutine or a sub-problem that you have to solve before you go on and do something else. So this is not really that difficult, but then what that means is, say you're sitting down, you are writing some other algorithm, and you say, well, the first thing I want to do is grab the connected components. How long is that going to take me? Well, here's a good estimate if you don't have a more clever way to do that. And of course, this is just a straightforward solution with knowing nothing else ahead of time. If you have some other prior knowledge, you might be able to do it a little bit more clever than this. Or if you store, depending on how you implement your graph, if you store your vertices in a particular type of data structure, you might be able to recover connected components rapidly, even as fast as constant time. Here I'm just assuming a very simple standard, maybe implementation, and you actually have to carry out the algorithm to extract the components. Okay, so continuing in sort of the vein of some of the easier problems, simpler problems, the second one I want to look at is the idea of detecting a cycle. And again, the reason I wanted to bring this up is because the solution to this is actually going to be the same. We can run a depth first search, at least if we don't have any other indication of how we might solve this problem. So again, here I've characterized my problem sort of as a decision problem and as a non-decision problem, just for the purpose of characterizing the distinction there. My first one is just saying yes or no, sorry, does the graph have a cycle or not? The second one is going to say, well, if there is a cycle, tell me which vertices are in that cycle and the order that they're in that cycle. I could have also asked for the edges here. Those would be equivalent as opposed to the vertices. However, it's possible that no cycles exist, so if no cycles exist, we need to still have that special case saying no, the error case, there is no such cycle. So again, how might we carry out this, or how might we solve this? I mentioned depth first search would be another solution. How can we do that? Well, if there's sort of two sides to this. One is, again, if we do our depth first search, and in our depth first search we never encounter a vertex that we have already encountered, a repeat, except through backtrack, then there must be no cycles at all in our graph. So the no side here is, if you do your depth first search and you never repeat a vertex, then you should say no. If you do a depth first search and you do repeat a vertex, well then what you've detected is a cycle, a way to start at a vertex, follow a sequence of edges, and get back to that vertex. And so if you can do that, you just grab that sequence there. You've got this remember, if we're in this subproblem where we want to recover the cycle, you stop when you get to that repeated vertex, and then you just backtrack until your last occurrence of that vertex, and that will be your cycle. So we could again use that depth first search as our sort of backbone, even if we want to recover the cycle with a little bit of modification in there afterwards to recover it. So again, these two problems sort of are closely related. And again, without being more clever, having something else that we could use to do that, we might just use our depth first search and take order E to do that. Now, I keep saying maybe we're a little more clever. What do we mean about being a little bit more clever? Well, first of all, the connected problem and these cycles problems, as I've already sort of mentioned, are often used maybe as a first step or a subroutine in other algorithms. So they're not really a problem that we face on its own. We might face it on our way to something else. And so then, because we often have an ulterior motive or a different purpose than just finding cycles, we might have already structured our graph ahead of time with preparation to do this, meaning maybe we're storing again our vertices in a particular type of data structure that makes it quite easy to identify which, say, connected component each vertex belongs to, or again, an algorithm that I sort of have in mind is one like a Prim's algorithm, or sorry, a Kruskal's algorithm, where we maybe merge trees together. We know we don't create cycles because we're always merging two trees together. We're never connecting two nodes in the same tree. If we connect two nodes in the same tree, we might know that we're creating a cycle. It might be much easier for us to find that cycle and detect that cycle ahead of time, given that we have some other, other information that we can bring to bear now. So again, the last problem and this problem, when I say bring our depth first search in, it's saying assume you don't know anything else. You're given just a graph at face value, no other promises. If you are given some other promises, you might be able to be a little bit more clever. Okay, so these first couple problems are pretty straightforward and easy to solve. And I wanted to just mention that related to them, and this is closely tied to our definition of what a forest and a tree is. In my previous video talking about terminology, I mentioned that we can define a forest or a tree effectively as being a graph with no cycles. Trees just add the extra layer that it should be connected. And so here I've just again stated two problems. Yes, if it's a forest, no otherwise. Yes, if it's a tree, no otherwise. The only other addition here is I've added the term connected to the input, saying that my input to the tree problem should already be connected. If it's not, remember that was the earlier problem, so here's where this might be a subroutine. We start out, we check if it's connected. If not, we say no. Now forests are disconnected. Every tree is a forest, but not every forest is a tree. And so we don't have that criteria up ahead of time. Again, depth first search, because of this tie here to the cycle problem, here I'm claiming these are sort of the complement to the cycle problem, depending on how you frame your cycle problem. So detecting if a graph has a cycle, well, if you detect it has a cycle, then it must not be a tree or a forest. If you know that it's a tree or a forest, then it must not have a cycle. So we have this sort of back and forth relationship between these two problems and the cycle problem. Also related to these two problems then is a more common problem, which is the minimum spanning tree problem. And in another video, I'm going to talk about solutions to that. There's a number of different solutions to the minimum spanning tree problem, so I won't talk about that here. But here, a minimum spanning tree. Let's just look at the problem itself. Again, upgrades from our previous problems, we've added a weight function now. So now it's a weighted, connected, undirected graph. Again, why am I assuming it's connected? If it wasn't, then there is no minimum spanning tree. But if I assume that it is connected, then I know there's a minimum spanning tree. Okay. In addition, what do I want then? Well, because it's a minimum spanning tree, we're talking about an optimization problem. So we've got an M for the minimum. Okay. And then a tree, a T. Now what makes it a spanning tree is that V is the same as our original V. All the original vertices appear in our underlying spanning tree. So here we've got the spanning tree, but we might not have the same edges. Okay, we are eliminating some of the edges. Now, what makes it the minimum spanning tree, of course, is that it has the minimum weight m, when we add up all the weights of all the edges. So again, this is another algorithm, or sorry, another problem for which we have a collection of different correct algorithms that we could run for it, and all of them have, you know, sort of slightly different analyses that we want to be careful about, subtleties in the analysis, but most of them have pretty efficient run times, so choosing among them is a little bit of choosing your favorite. Another very common problem that you'll encounter with graphs is the shortest path problem. It's a common problem. It's so common problem that you probably encounter it on a daily basis if you're out driving or navigating. We now all pretty much rely on a Google Maps or similar program to calculate the shortest path in time or in distance between 2 points. And the way it solves it is by treating the map, the transportation network that you're going to drive on, as a network, as a graph of nodes connected by edges, roads. And so it will plot your course by solving or running an algorithm on that graph and using the solution or offering the solution to you as the shortest path. Now, here I've got the problem stated. This is actually a simpler version than that Google Maps problem that I just mentioned there. In this one, all that we care about is the number of edges in the shortest path. So here I've got some path of vertices from S to D, and I want to minimize the number of edges that I have to traverse along the way. Now this is the shortest path problem if we have a couple possible promises about our graph. One, there's no edge weights. In this case, I have no edge weights. Or maybe we do have edge weights, but we have a promise about the edge weights. One, maybe the edge weights are all 1. That's sort of like having no edge weights. Or the edge weights are all a constant, but the same constant. Or a slightly more complicated condition, which is that the cost of the path is a non-decreasing function of the number of edges. That's sort of a fancy way of saying that the cost of the path is basically the cost is effectively the number of edges plus some fudge factors on there. But in that case, if that's the case, then we can actually rely on a simple algorithm to solve it, the breadth first search algorithm, which again, we already mentioned, its runtime is order E. And that's because breadth first search iterates through the vertices by starting at the source vertex, the one that you start at, and then first encountering all the vertices that are 1 edge away, then all the ones that are 2 edges away, and so on, sort of spiraling out until you encounter the vertex, the D, the destination that you're trying to get to. Now, if we add our edge weights on here, we can get a slightly different problem. Here, now we're going to be adding up the weights of all the edges as we go. Okay, so again, we're going to have a path, but now we're going to add up the weights of all the edges as we go. And this, now M is the sum of all of those weights. K may be some other value, is the number of steps that we have to make, the number of edges we need to transition through. Now, this problem is sort of our more standard problem. This is the more Google Maps version where our roads have different lengths, so they get labeled with different weights. And we've got an extra little promise I've added here, which is that we don't have negative weights. And that's because the problem actually gets a little bit tricky when we start adding negative weights in there. And I don't mean tricky to solve. We do have solutions to that as well. But we get some interesting graphs now where the shortest path is negative infinity by spinning around and around a cycle over and over again. And so because that is causes a little bit of trickiness in the definition of the problem, I'm just going to eliminate negative edge weights altogether in this definition. This is a variant. There's many variants actually of the shortest path. These two are just two of them. This particular variant might more commonly be called the single source, single destination shortest path, because we state a single source and a single destination, and we just want to know the shortest path between them. This raises the possibility of other possible problems we could talk about, shortest path problems. And it turns out a common solution to this problem, which is Dijkstra's algorithm, it solves a slightly different problem. It solves this problem for us, but it solves a more general problem, which is the single source any destination shortest path problem, meaning it doesn't just find the shortest path from S to D, it finds the shortest path from S to every possible D. And that maybe is something that you might want to solve. Now, again, I raise this because if you're, again, the Google Maps problem, if you're using Google Maps, then you're probably just at an S and you just want to get to a D. But if you're Google and you have a bunch of users, they are trying to get all over the place. So Google might want to solve a more general problem like single source all destinations. And in fact, that in the long term might be something that you would like. Say your single source is your house, and it calculates the shortest path to everywhere you might go, your favorite restaurant, your work, your school, wherever you might need to go. It finds you the shortest path there, and then you might need that. You might want that stored so you know how to get anywhere you want to go quickly. Now, Google, on the other hand, doesn't just have to worry about where you need to go. They want to worry about where I want to go, where anyone wants to go. So they actually solve an even more general problem, which is we call it the all pairs shortest path problem, or we can think of it as the all sources, all destinations shortest path, which is we want to find the shortest path between all the possible points, pairs of points we could have. And we might think of Google Maps as solving, or Google as solving that problem for the Google Maps software, because they want to be ready at any point. Whenever anyone types in their destination, they want to have already a solution available saying, here you go. Okay, so just a little highlight foreshadowing there. Google does not, when you ask for the shortest path between 2 points, they do not go and run a solution. That will take too much time. They've already done that ahead of time, and they have that solution stored somewhere in a giant hash table for you, and they recover it for you. Okay, so that's just a comment on variance on the shortest path problem. There's more than one version of it, so be careful when you see it. Don't just say, "Oh, I know shortest path." Say, "Hey, which shortest path problem is it, and which algorithm is going to be best for solving it?" Okay, I want to continue with a couple other interesting graph problems that have some real-world versions. This first version has to do with a once Prussian city of Konigsberg, which is now a Russian city named Kaliningrad. But this city is over, a river passes through the Pregel River, and so there's a number of bridges over this river that connect various land masses. And here's sort of a rough diagram of it. And these are 7 famous bridges of Konigsberg. And in 1735, the city wanted to promote tourism to the city, and they wanted to do that by advertising a 7-bridge tour where you would start somewhere at your hotel, presumably, and you would walk through the city visiting every one of the 7 famous bridges, and at the end of the tour you would return back to your hotel. And the goal of the tour, or the hopes of the tour, is that you would never have to walk over any of the bridges more than once. You don't want to have to go any further than you really need to. And so you can imagine being maybe a member of the city council and looking at your graph here and saying, okay, I'm going to start here, walk over here, and you go, oh, I got stuck on riverbank B. Okay, start over here, go over here, and oh, I'm stuck on island D. So as you try them out, you continue to fail, and you might start saying, well, gee, maybe I'm just not smart enough. Maybe I need someone smarter than this. So this is what happened for the people of Konigsberg, and they reached out to the most famous mathematician of the time, Leonhard Euler, and they said, okay, Euler, can you help us with our problem? You're smarter than us. Can you find a tour? And Euler wrote back and said, no, I can't. But he wasn't just being sort of obstinate and saying, hey, I'm not going to help you. He actually went further than that. He said, okay, no, I can't find your tour, but because no such tour exists. And Euler, a mathematician, didn't want them to have to take his word for it, so he decided he was going to have to go and prove it. And his proof and his effort that he put in there helped to start graph theory, which is what we're talking about right now. And so here I've got sort of two versions of this problem. The Euler cycle version is the one that I just sort of mentioned. Here you've got some graph where you're going to want to find a permutation of the edges. The edges here represent the bridges, right? And we're going to want to figure out the order in which we would visit those edges, constituting a cycle here. So we have to end up starting and ending at the same location. So if I could find that, because it's a permutation of the edge set, that means all the edges are there. So that's the visit all the edges exactly once bit. Okay. And if it's a cycle, meaning we're not cheating by jumping from island C to island D without going over a bridge, then we want to know what that cycle is. We want to know the order. Otherwise, we want to output no. Now, remember, there's a decision problem version of this. I just don't have it stated here. That just says yes or no. Yes if the tour exists, no otherwise. But of course, the people of Konigsberg, if the answer was yes, want to know what the tour is. They don't want to just have the answer yes. Now, the Euler path, the only difference here is that we've changed the definition from cycle to path. That means you don't have to start and end at the same location. So you can imagine after Euler came back, he said, no, there's no such possibility. Well, maybe they would come back and say, well, what about a path then? What about if we don't have to start and end at the same location? Okay. Well, we were still getting stuck earlier when we were trying it. And it turns out that Euler came back with two theorems, if you will. Theorems about when you could expect to find an Euler cycle or an Euler path in your graph or your town, if you're doing this for your town. So we first said that an Euler cycle is only possible in your graph if and only if every vertex has even degree. Okay, so here A, B, C, and D, those are my vertices here, but you can see bank A has 3, bank B has 3, island C has 5, and island D has 3. It turns out every vertex has odd degree. That's like the worst possible case scenario. And he even came back to say, well, if you want a path only, well, then you're only allowed 2 odd degree vertices, and you need to have exactly 2, and those are where you start and end. Okay, you start and end at those ones. Again, not possible for Konigsberg. So unfortunately, Konigsberg, no good solution here. Unless you change the graph. So, maybe Euler said, hey, it would work out fine. All you need to do is blow up this bridge here, and then you get a path. You could walk all the way across. Of course, that's probably an unsatisfying answer to the people of Konigsberg. They like that bridge. They use that one, so they don't want to blow that up. So maybe a better suggestion would be, well, build some more bridges. And in fact, with one more bridge, they could get a path. And I think it takes 2 more bridges to get a cycle. In addition to providing these proofs that he created, Euler also created algorithms. If you did have a graph or a city that was able to create such a tour, he showed you how you could do that. And it's actually an interesting one where you have to find cycles. So it's a case where our earlier problem sort of becomes a sub-problem of the algorithm that Euler has presented. Another sort of interesting problem, very similar to Euler cycles and Euler paths, is called a Hamiltonian cycle or Hamiltonian path, named after the Irish mathematician William Hamilton. He created what he called the Icosian game, which is he built out of a dodecahedron. A dodecahedron is a 12-sided polyhedron, or three-dimensional shape, as we've got here, or a 12-sided die if you happen to be a gamer or a Dungeons and Dragons player. And he had a shape like this, and probably larger than a die, where he would put a pin in each of the vertices. And then the goal was to take a piece of string and sort of try and visit all of the vertices on the dodecahedron and return back to where you started. And the game, the sort of underlying game that he invented, he said it was sort of around the world, visiting all the cities in the world, where each of the pins was like a famous city. So he'd labeled them like Paris and New York and Beijing and so on. And you would, and so the goal was to sort of play this game. Now, this game, of course, was just could you find one? Now, on the dodecahedron, if we treat each of the vertices as, or each of the points as a vertex and each of the lines as an edge, we can draw a corresponding graph. This is the corresponding graph here, and we can kind of see if we've got the first sort of pentagon here, and then each one of these pentagons is the one sort of on the side here, and then the outer pentagons are the ones that we can sort of see in the back there, the see-through ones, and then the outer pentagon, the biggest one, that's the one on the back. And so this is just sort of a two-dimensional drawing of this same graph that's drawn in 3 dimensions here. And remember from our last video, we used a term, we called it planar. If you could draw a graph so that none of the lines cross over, if we can draw it in 2 dimensions, that is, then it's planar. So this shows that this drawing of the graph here is isomorphic to this one here, but this drawing of the graph is drawn in 3 dimensions where no lines cross over, but in 2 dimensions, the way we've drawn it, lines cross over, right? But by reorganizing our vertices, we can draw it in a planar form where none of the lines cross over, and that might make it a little easier in 2 dimensions to play the game. So start at any vertex and see if you can find yourself a tour. And of course, spoilers, of course, one exists, or else this wouldn't be a very fun game, right? So see if you can find one. Here's one, okay, just sort of highlighting it. Of course, there's more than one, so that made the game a little bit replayable as well. Now this particular graph has a solution, so the problem is find it if it exists. But some graphs do not have such cycles. It's pretty easy to create a graph that does not have one. I'm just going to create what I call a handlebar. I'm going to take a vertex and attach it here with one edge. Well, because it's dangling off there, you can only enter that vertex, and then you can't sort of leave it again except by the same edge, meaning revisiting the same vertex again. So some graphs have Hamiltonian cycles, others do not. Again, we can define 2 problems, cycle or path, whether we are talking about a cycle or a path. Every Hamiltonian cycle is also got inside it Hamiltonian paths, but not vice versa necessarily. And it turns out that unlike Euler's Euler paths, Euler's problem, he found a solution to it in an algorithm, a pretty efficient one. This problem is actually notoriously hard to solve if you have a large enough graph. And that's because our best known solution is exponential time. These 2 problems are examples of what we call NP-complete problems. And an NP-complete problem, our best known solutions are exponential time. So these are actually hard problems compared to our Euler path and Euler cycle problem, which is actually fairly easy. Okay, however, for a small graph like this, it's not too hard. A closely related problem to the Hamiltonian cycle problem, actually here the way I've got it depicted is as the Hamiltonian path problem. This is what's called a traveling salesperson problem, or the traveling salesperson path, or a traveling salesperson cycle. This is the problem as executed on the map of the United States, at least the contiguous United States, where the goal is to visit every state. I believe it's every capital of every state. I'm not an American, so I don't know all of the capitals of all the states. But as far as I know, looks like all the capitals of all the states. And if it is, then if not, it's visiting at least one city in all of the states. And the goal of a traveling salesperson path or cycle is to visit all of those, in this case vertices, cities, with the minimum cost distance to travel. And so that's the minimum total edge weight of the cycle or the path. And so this is actually one solution, or the solution, given the roads that you could travel on in the United States. At least this is one I found online on Reddit. Again, we could define this problem two ways as a cycle or a path. I've just sort of defined it one way since it's very similar. Another related problem, if we were going to continue talking about sort of the United States here, here's another problem that you may have encountered if you lived in the United States as a child. Then maybe you were given this map and you were given the coloring assignment of, well, you have to color every state on the map a different color, or not necessarily a different color, but so that no two states that share a border have the same color. Okay, and this is a common coloring problem for maps. You want the next door neighbor states to stand out from one another, so you will assign them different colors, usually contrasting ones to make it easier to see. And then usually you're going to want to use the fewest number of colors so that you can maximize the contrast between two colors. If you end up using 100 colors, you're going to get a lot of shades of red in there that might be hard to tell apart. So even two neighboring states, if they have the same or are both red, might be hard to tell apart. You want to maximize contrast by minimizing the number of colors. So it turns out that this problem again can be turned into a graph problem, where instead you've got a graph where here each state is going to be a vertex, and we're going to put an edge to any other state that it has a border with. I live in Washington, so Washington would be connected to Idaho and Oregon. And so if we could create a graph for this, for all of the 48 states, let's ignore these two for a second, then that graph would have certain edges on it, certain states would be connected to one another, and then we could define our coloring problem, the map coloring problem, as being assigning a color to the vertex. Okay, so here I'm saying giving yourself a color function, C of V, that you pop in a vertex, and it gives you one of m colors, where m is minimized. Okay, one of m colors, such that, and here's our rule, if you have an edge between your two states, your two vertices, then their colors better be different. Okay, and so again, here's sort of a solution to that type of problem, where we've colored it with, I don't think this is absolutely minimal, but it does try to minimize. And it respects a couple things here. It respects, actually, this is sort of a bizarre combo here. I've never been there, but I've learned from at least some of my American students that there's actually a point here you can visit where there's, I guess, a pole or something sticking out of the ground, where if you sort of hug that pole, I guess, you can simultaneously be in 4 states at the same time. And so that's sort of interesting. And if we want to respect that, saying that Utah borders on New Mexico and Arizona borders on Colorado, then we would want all 4 of those to have different colors. However, if we don't think sharing a point means sharing a border, then we could use 2 colors to color those those 4 states there. The graph coloring problem is a very interesting problem. It's tied into other problems as well, and it has some interesting solutions. One interesting solution is, at least for maps, that is, if you've got a map on a 2-dimensional surface that, for the moment, I'm going to wave my hand and says is well behaved, then you should be able to do this with only 4. Okay, now again, a few assumptions is we don't count points. We won't allow points as being borders, because if we allow points, then you could make like a sort of like a pizza pie like country or a continent where all the states visit in the middle. And you could have any number of nodes connecting any number. But if you don't let them connecting in the point, and you create that weird pizza pie like country, this is sort of a pizza pie with 4 pieces, right? You could only ever, any node can only ever touch 2 others, the 2 neighbors in the pizza pie, right? And so there's this interesting result that if you are on this two-dimensional world, you only actually need 4 colors to color, and it's related to planar graphs and how many nodes you can connect to each other in a planar graph. And I said also if you're well behaved. Unfortunately, this map I have here of America, the United States is not a well behaved country. Mostly by well behaved, I mean any one state is sort of self-contained, but America has Alaska, which between Alaska and the rest of America is Canada, and that's where I'm from, so it's kind of important to me. And if you want to color America the right color on a map, you want to make sure that Alaska is colored the same color as the rest of America, because it's part of the same country. And that actually causes some problems. Once you allow a country to be sort of divided up into different chunks in different parts of the map, it introduces more bizarre problems to your coloring problem, and that would actually just sort of change the problem as it's defined. Now, well, that's sort of the real world version that we apply abstraction to arrive at this graph coloring problem. Okay, so I think that's all I'm going to say about coloring, but graph coloring is another hard problem for a graph in general. Okay, if we're given promises about the graph, like maybe we could draw it on in 2 dimensions, sort of like this, then maybe it's a little easier to solve. Okay, I want to finish with 3 final problems that are related to subgraphs. And the first one here, clique, is actually closely related to the coloring problem here, and let's see why that is. So the clique problem is given an undirected graph, and actually it's given an integer here as well, but I'm going to skip that for a second and just focus in here. It's going to say yes if there exists a complete subgraph. Now let's focus in on this. Subgraph, remember, being just any old subgraph, select some vertices, select some edges. A complete subgraph means one that has all the edges in it. Okay. Now I mentioned, why does this tie in to our last problem, the graph coloring problem, is because if you have a complete subgraph in your graph, that's where every vertex is connected to every other vertex, then all the vertices in that have to have a different color. Every one would have to have a different color because everyone is connected to every other one. So these 2 problems are actually closely related. And this problem, I mentioned the k here, is just going to ask, can you find such complete subgraph of size k? Or greater, technically, because if you found one bigger, you found one of size k. Okay, so this problem is just asking us, can we find a subgraph that's complete, that all the edges are in it? So if the whole graph was complete, that would be an easy answer. Yes, we can. Now, really, all it's doing is it's saying, can I ask the graph, or the problem is asking of the graph, does it have a subgraph that matches some property? And switching from clique to independent set is just saying all the edges are there, to switching that to none of the edges are there. Can we find a subgraph of G with no edges, also of size k? So the k is performing the same role here. Okay. So again, just asking, is there a subgraph with this particular property? Now, subgraph isomorphism, I've highlighted this as a problem because this is sort of this is a more general version of both of these problems. Here, we're given 2 graphs, G1 and V2 or G2. Again, all I'm asking of them is one of them isomorphic to the other one. Well, a slightly different problem, which is graph isomorphism, not subgraph isomorphism, just says, are they the same graph? Are they isomorphic to each other? And if they are isomorphic to each other, that means they're the same graph for most purposes in graph theory. However, subgraph isomorphism is asking actually a more difficult problem. They're both pretty difficult problems, but this is a more difficult problem in that it's saying take any graph, subgraph of G2, and is that isomorphic to G1? So subgraph now means you're not just comparing two graphs to see if they're isomorphic, but now you're saying, is G1 isomorphic to any possible subgraph? Meaning you have to go and compute for all possible subgraphs of the appropriate size, are they isomorphic? So it sort of increases, maybe adds an order of magnitude to the problem there. So the reason I wanted to bring up this subgraph isomorphism problem is we can see clique and independent set as sort of being special cases of this, where what we could say is we have our original graph G2, the one we're asking a question about, and then the graph G1 that we pass in is a complete subgraph, or a graph with no edges, or a graph with some other property. If you want to do cycle detection, we could pass in a cycle. Tree detection, we could pass in a tree. There are other different sort of interesting other problems rather out there that have basically are just special cases of subgraph isomorphism. So what that means is if we can solve subgraph isomorphism with a real cool algorithm, we could go back and solve all those other ones probably with the same algorithm. Now, with that said, these problems are also examples of challenging problems, NP-complete problems, and so they don't have really slick algorithms for them, okay? Even though solving these problems might be something that you need to do or you might want to do for whatever purpose that you need to put them to. Okay, now I don't know how many graph problems I went through in this video, definitely close to a dozen I imagine, but there are dozens more, so there's many that I've left out. I've only selected a number that I thought were interesting and that I thought were maybe more common than others. Some of these problems I am going to look at some algorithms for in a future video. Others I'm going to try and compare to one another for the purposes of doing complexity theory comparisons, comparing them for how complex the problem is to solve. And that last little bit about these problems being NP-complete problems, that's exactly what I'm talking about. So if you're interested in that, stay tuned. Thanks a lot for watching, and we'll see you in the next video.